Hello world, my name is David Malan, and I'm here, of course, with
Colton Ogden.
And this is our second of two live streams today, this one on CS50 2D, the new and improved version of CS50's introduction to 2D game development. I'll be fielding any questions via the chat if I can, or raising my hand on your behalf. This course will be live on edX later this year, as will the assignment, so watching now offers a bit of a preview. And please forgive, as always, if we start and stop to fix things along the way. This is very much a live lecture. So we've been doing some fun facts each day, and they're getting harder to come up with fun facts. But I'm thinking this. Right now, people will be familiar with today's topic probably in the form of a mobile app nowadays. And I wonder, what is your go-to mobile game these days, if any?
I don't mobile game at all, but I think funnily enough, in an airport not too long ago, it was Candy Crush, literally their newest version, like Candy Crush Soda or Pop or something.
Oh, interesting. I can't remember if I'll have to check my history if I've ever installed Candy Crush.
It's addictive. I mean, I respect the formula. It works.
Yeah. All right. Well, more on that today. We'll be back in a minute to begin class. Thanks.
Hello world, this is CS50 2D. This is week 3, and this week we're going to take a look at a classic game that a lot of people are probably familiar with in recent times on their phones. It's called Match 3. Well, the genre is called Match 3, and the game probably originally in its most famous initial incarnation started with a game called Bejeweled. It had a predecessor for DOS back in the 90s. But Bejeweled was a game that was very popular. I remember playing this in the 2010s, circa 2012, 2013, quite a bit, as a sort of addicting game that was kind of easy to play on phones or just on the computer, what have you. And it's a very simple formula, really. It's literally in the name, which is kind of funny, but essentially it is, you have this grid of tiles. They can be whatever you want. In this particular case of Bejeweled, it's themed after jewelry. And I think the sort of the more glitzy or appetizing the theme is, the better, typically for engagement. But in this case, we have various jewels of different colors. They're very individually recognizable, and they're all arranged such that, you know, essentially they're orthogonal to one another. You can swap any two that are directly adjacent to each other. And what you get from this is, essentially, once you have, let's say these examples up here, these orange and blue gems, if you were to swap these two together such that now you have 3 contiguous orange gems, well, now you've completed a match, and then you'll get some points for that, at which point the tiles will replace to fill in the gap that gets created from those gems, and there's all sorts of other effects. More people probably nowadays are familiar with Candy Crush, and I've even played this relatively recently. And it's also the same exact idea. In fact, if you were to go between the two of these, they're almost indistinguishable at a glance. Except this one being a little bit more candy themed. But if we think about last week, we talked about sprite sheets, we talked about breaking a texture apart into these individual tiles, and this in some ways is a continuation of the same ideas that we looked at last week, but we'll also be looking at a lot of other very interesting ideas. In particular, tweening and timers are the two biggest ones this lecture iteration. We looked at anonymous functions in Flappy Bird when we introduced the state machine and the ability to have anonymous functions instantiate the states within that. But in this week's lecture, we'll look at that a little bit in a different use case in conjunction with tweening, which is essentially just interpolating a value between 2 points. Timers, which will allow us to perform that, but allow us to do lots of other very interesting things, to think of our game as a set of operations over time for things that should animate or transition smoothly. Up till now, we've only been doing essentially automated movement based on velocity, dx and dy. Things have been otherwise very discrete and very instantaneous, and as a result, we don't have that fluidity of motion that allows us to do certain things like transition things from one spot to another. So we'll be able to do stuff like that. We'll look at how to solve matches, which is the key to match 3. How do we detect that a match has actually happened and then replace those tiles in the grid? We'll look at how to fill that grid up with tiles, and we'll look at how tiles and ID sort of map one-to-one in this version of how we're going to implement things using quads, which we looked at last week, tile sheets. And then lastly, at the very end is a little bit of fun. We'll look at sprite art and palettes, which is another detail that is really important in the aesthetics of a game and which we're capitalizing on this week with our sprite sheet, which we, as you can see here through a few previews of what our goal is to implement today, we have a somewhat feature-rich game example implementing the same exact principles of Match 3 using its own version, its own tile set therein. But I think it'd be nice to actually get a chance to take a look at what it looks like, and I'm hoping maybe if we could get a volunteer to come up and take a look at the game and try it out. Oh, sorry. I guess probably.
I'm so sorry.
I guess we should have probably.
Yes, I'm sorry. I'm supposed to be sitting in front for that.
I should have primed that. I'm sorry.
That's okay. Let me come up and we can cut this together.
Yeah. Let me also make sure that that's ready quickly to go. Okay. Okay. Sorry. I was realizing as I was saying it, I was like, oh shoot. I tried to slow my words down a little bit and to get your attention.
Yeah. No. Totally.
That's my fault. That's my fault.
Can we use this? Can we use the same words Colton said, or do we have to redo that?
Okay, can we have Colton please stay at the lectern?
Oh yeah. Okay. That makes sense. Yeah.
I think I can just come up, right?
Yes.
Do you want to joke again about not knowing your name, or?
Yeah, sure. Let's do that.
Okay.
Make it a thing. Okay, here we go. Ready?
Yes. I know this.
What?
Oh, I think we went.
Hi.
Dan, right?
No, David.
Oh,
David,
okay.
yeah.
Nice to meet you. Nice to meet you. Okay. So I'm going to go ahead and run the code here.
Okay.
This is this week's final example. All yours. So arrow keys will move between start, quit game, and enter to hit to start the game. Notice we have a transition to white. We have this moving thing transition as well. So the controls are arrow keys will move your cursor around.
Okay.
And then if you press enter, you'll select a tile to swap.
Okay.
And then you can swap it with another tile adjacent to it, directly orthogonal, left or right, top to bottom. So then so that will click it in place. So then you want to move to the tile that you want to swap to.
Oh, so click it once.
So you had it selected there. So now you have that one selected. So now you
Okay.
can move into top right, left, or
I
bottom.
don't think I'm playing this well.
And then you can move those two. You can swap those two if you wanted to. Okay. And so we have the swap operation performed. Notice they happen sort of smoothly. They tween positions.
Yeah. Okay. And I can do this one now.
Yep.
Oh, I think I know what I'm doing now. Oh.
Oh, subtle color. That one's a purple color and that one's
That's
a pink.
pink.
Color. Very subtle color difference. It's in the highlight here. This particular sprite sheet has
Fine.
a couple of colors that are very similar.
All right. I'm gonna move this one up. I'm gonna move this one up. There we go.
Amazing. And then tiles.
Very nice.
Notice the tiles move down to fill it in.
How did I lose? I just won.
It's balanced a little bit for high scores, but it's we have all the pieces here for match 3. But thank you very much.
Well,
Appreciate
thanks
it.
for having me.
See you next time. Go ahead and press enter there to restart it. So I think we saw a bunch of interesting pieces looking just at that example. The biggest pieces that jump out to me, and I think the pieces that are going to be relevant for this week's lecture in particular, that transcend just this lecture, are the transitions themselves. So I'm going to restart the game just so we can look at a couple of pieces real fast. But we'll notice, one, right off the gate, match 3, the letters are rotating their colors on a timer. It's very fast in this case, but it is operating on a timer. The background is scrolling, but that's not anything related necessarily to this week's lecture. But if I hit start, we'll notice that we fade to white and then from white into a new state. And then we have this transition of this, or rather this translation of our level text to the middle of the screen and then off screen, so this Y position interpolation. You'll notice also in this box of text to the left, we have a timer which is counting down to 0, at which point this current level will end and the player will lose the game. If they were to go over their score of 1250, they go to level 2, at which point their score threshold will be higher for them to not lose effectively. And as we saw, even moving 2 tiles, they don't instantly switch positions, they interpolate between the 2 positions. And the same thing were to happen if you were to watch the match occur here. You'll see that the space gets filled by the tiles above it, and also the new tiles that come down will interpolate into in this case, their Y position. In all cases, their Y position. But there are a lot of sort of similar pieces there, but they all come from the same idea of using interpolation, using tweening, and using a timer. We've done everything based on automatic sort of position calculations using physics in the case of Breakout and Pong. And in the case of Flappy Bird, we did have gravity applying to the bird, but the pipes were moving sort of like on their own from right to left. But also, the way that the pipes were generated was a sort of primitive version of the timer that we'll end up looking at. And so I think in order to set the stage for us going forward, before we even get into the timer stuff, I think it's important that we have a little bit of a review in terms of the quads that we looked at last week with Breakout. That was one of the bigger themes of last week's lecture, last lecture, Breakout, and that is this idea of having a larger image that you can then slice up and then draw an individual piece of that texture. So if I were to go to my source code here, I'm going to go ahead and close out this match 3 main repo here. And then let's go to quads 0. Quad 0 is very simple. In fact, it's not really anything that people haven't seen yet. But here, to start us off with, is just the texture that we're working with. And in the case of last week, we saw with Breakout, there was a texture that was similar to this. It was a texture atlas. It had a lot of different types of elements on it, whether they were bricks, they were paddles, they were the balls or the hearts, different colors, different arrangements, different sizes for the paddles. Chopping up that texture was a little bit of work. This particular week's lecture, we're only using one texture, and this texture is uniformly the same size for all of these tiles they're in. These are all 32 by 32 tiles, and we can split this up into one just singular array or multi-dimensional array if we want to, based on color or based on the rows, and they're all just 32 by 32 pixels. So in some ways a lot easier to deal with and think about than last week. But you can also envision that each of these individual tiles could therefore, if we're just chopping it up into one array or table, 2D or singular dimensional, they all can just get a number, an ID essentially, that maps to whatever that tile is. And then that allows us to say, oh, okay, which 3 numbers maybe are the same that are contiguous, or so on and so forth. So I'm going to go ahead and look at quad 0 here real quick. This is a very simple example. I'm going to run it. We'll see that it literally just prints the texture, because the goal is for us to get started. Just what do we have to work with? Where are we moving towards? So this is just literally drawing the texture. It's nothing that folks really haven't seen yet, but we're loading it. We're getting things ready to go. Just a very simple love.graphics.draw of the texture. Now, as we saw last week, if we wanted to draw a simple piece of that or an individual piece of that texture, we need what's called a quad. So if I go ahead and go back to the code, and let's go ahead and open up quads 1 now instead of quad 0. We can see that we have, as we used last week more or less, a single quad at the top left of the screen. In this case, literally just the first quad of the texture, the first rather sprite or element or texture image within the actual atlas, which is just the singular block at the top left. Recall, if we were to just open the texture again, it's right inside this same folder. It's the same, just simple, sort of khaki colored texture, tile. In this case, if we remember from last week, we can take the same image and then load the same texture and then draw it kind of largely the same. But now we're going to create a new quad, which is from 0, 0 on the x and y to 32, 32 on the x and y. So we're defining a 32 by 32 sort of square rectangle as our quad. And then if we come down here, remember, we can just draw quad as the second argument to love.graphics.draw, and that has the result of the texture gets drawn, but only through that window of that quad. So simple enough so far. Whoops, almost lost the clicker there. So quads 2, and caution for folks, this might visually look a little bit, might be a little bit intense for a second. I won't keep it on screen too long. But we can sort of, if we were to chop up our texture into all of those individual quads, right now in that last example, all we did was we just created one quad. But if we want to have this idea of every single tile in our game, we can generate every single quad per the generate quads function we looked at last week, which is in this repo as well. We can store all of those into a data structure and then index into it, index into this table, this array. And then the index is effectively just the ID of the tile, right? If we open up in this case, let's open up, we can look at this texture. But if we imagine that this is ID 1, if we were to break up this whole texture into just one large array of quads, each of them are 32 by 32, then this one at the very top could be ID 1, this could be ID 2, 3, 4, 5, 6, and then 7, 8, 9, 10, 11, 12, so on and so forth, if you were to just iterate throughout the entire chopping up of your texture into quads. And that's essentially what we mean by an ID whenever we're trying to draw some kind of a sprite or some kind of tile or whatever we want to talk about. This will be relevant especially next week too, when we get into Mario, into worlds and such. But these IDs, these indices into this array is effectively the way that we can think about these tiles as entities that are orderable or comparable. So, and also their color and as you can see, if we look at this texture, for example, we have these different colors that can be grouped into their own tables, their own subarrays, which have variance. In this week's lecture, we won't look at variance as a relevant factor. That's going to be part of the problem set. But you could imagine comparing that it's in this color range for equality, but then whatever the variant actually is on that tile, stored as a separate flag, is some sort of score multiplier or the like. So if we go to quads 2, and caution again, this is going to be visually kind of a lot, but I'm just going to do it very briefly for a second, and you'll see a texture, rather the set of quads very rapidly changing on the screen. And so in order for us to have this idea of a board of tiles that's consistent, right? It's one thing to draw the tiles, but it's another thing to actually have a board that's a data structure that we can compare tiles within and actually have some persistence, right? We can draw quads, we can draw rectangles, we can draw the texture, but we need some persistence. So this is illustrating the first step towards, I guess, that idea, is illustrating that things aren't persistent now, but we can draw at any point in that quad table any given quad. So let's go to quads 2. And then, so we'll notice the one big thing here is rather than just creating an individual quad, we're going to use that generate quads function that we had previously. And if I embedded it here just at the top of main. Typically this is in util.lua within each project. But all we're doing is we're essentially saying, given a texture and what's the width and height of the tile within that texture, we're assuming a uniformity of size for all of the tiles rather. And this applies to animations, various other things we'll see later. But we're going to get whatever the width and height is in tiles of this texture, and then we're going to create this quads table that we're just going to, using a 2D loop for every y going, every row throughout the entire texture, every column within each row, we're going to create at quad counter within quads that new quad that's effectively essentially the representation of this tile, the window of looking at that tile in our texture, and then just increase quad counter, and then we're storing essentially just all of the quads that make up the entirety of that texture. And then as a result, we can then just randomly choose any one quad to draw per frame, and you see the result on the screen. We have just this quickly going through all of these random texture, or all these random tiles, right? Because we're drawing it in the same place, we're drawing texture, but we're deciding to randomly choose an index within that quads table that we've created from generate quads. And in case we'd never mentioned it previously, this number sign is essentially how you get the length of a table in Lua. So we're just saying a math.random between 1 and the length of the table quads, so that we just get a random number each time. So cool. We have the ability to draw whatever random tile we want from that texture. Now we can sort of get closer to approximating our grid if we were to think about, okay, well, to create a grid, I need a random assortment, 2D assortment of tiles, so let's just draw that. Let's go to quads 3. And I should have probably prefaced that again with a warning, but yeah, warning for folks. It's very visually kind of intense, but that is, if we were to think about, okay, now let's draw over an entire range of tiles, not just the one corner, but let's actually pretend we're drawing a grid of tiles and then do the same thing. We are getting closer. So if we go to quads 3, we're using the same logic essentially, but instead of in draw doing a singular draw at the top left, we're going to go ahead and draw from 288 to 32 backwards, and basically from 0 to 288 going backwards in 32 pixel increments, and then 512. Sorry, that's from the y-axis going from top down to left to right. We're going to draw in 32 pixel blocks a random tile. And that's effectively what we're doing when we draw the board in the actual distro, except here we're not storing it. This is just ephemeral information, which ultimately isn't that useful because it's not preservable. We can't perform any operations on it, but we're getting closer to our end goal. And so that was full screen quads. And then lastly, what we want to do is we want to save these. We want to have these be persistent, because this is how we actually have a board state that is checkable. We can actually iterate through it and say, okay, this ID or this whatever we decide to store, this tile is equivalent in color or equivalent in tier to this particular tile. So if we go ahead to quads 4 and just run this, we'll see it's no longer jumping all over the place. We have a consistently rendered set of tiles, very cleanly fills the screen. And all we're essentially doing now is, well, the one piece left is we have to store, we're generating this random number every frame, but we just need to store it in place. And then if we store it in place in the data structure, we can just iterate over it, x over y, or y over x, and then just draw it the same each frame. So let's go ahead and take a look at that. In our love.load, you can see we have a tiles table. So this is where we'll store things. Same thing everywhere else. We do have a refresh tiles function, which is going to generate things. So if I reload this, you can see I can hit, I believe, spacebar to refresh tiles, call that same function. I have a key handler set up. And all this is doing is running that randomization, except it is storing them each time I do it. So I can effectively do the same thing, can almost imitate what we were just looking at. But we've essentially got our table now. We've got our, well, I say table. We have our data structure representing our game, our board state. If we come down here, refresh tiles is just going to store numbers, right? That's all we're doing. We're just storing the number of whatever that quad is that we want. And then we can just reference that number later when we do that two-dimensional iteration over our data structure down here in draw. We'll just say, draw the texture at quads at tiles yx, which we're using a 2D array in this case to store the tiles. So if we come up here as well, an important detail here is we're not just, an important detail here, should we refresh at a certain point? Do you want to restart at a certain point?
That's fine. Just when I hold things up, try just to read it without stopping.
Sorry.
That's fine.
OK, what did we have? on the screen.
Will you bring your audio down?
And an important detail here is that rather than storing all of these necessarily in one contiguous array, we can choose to store them in a set of arrays, an array of arrays, a 2D array, which some folks prefer to store it singularly, some folks prefer to store it in 2D. I typically tend to prefer to store arrays in 2D, but it's relatively simple math to convert between the two, and there are certain environments where storing it in a single array is going to be more performant. But in this case, we're going to store everything in a 2D array, and so to do that, what we're doing is when we refresh tiles, tile starts off as just this empty table here, but as we're iterating over y, going from 1 up until 288 divided by 32, which I think is somewhere around 7 or 8, what we can do is, oh sorry, that's 9. Yeah, I can't do math. But what we're doing is saying essentially from 1 to 9, we're going to insert a empty table here, which is going to then store that row of tiles. So at tiles y, we're then going to have this other table, which is the row there. So y being the rows, x being the columns. So at this row, we'll insert just some random ID. In this case, we're just math.random, the length of quads. And then what that will allow us to do is, as we come down here, we can just iterate over quads. Tiles yx is going to be the actual array, our 2D array. Our tiles are data structure for the board. Quads being our quads table of IDs. So we'll fetch the ID, link it rather, our table of quads that are effectively like thinking of our tiles like their IDs, which we'll do through here. So by offsetting into quads, we then are able to redraw the exact tile that maps to that ID, that random number between 1 and the size overall of our number of tiles. And you might want to adjust that to account for color and the fact that our color is spaced apart in groups of 6, for example, and 2 groupings per row in our Sprite sheet, which is tackled in the distro. But that's one consideration when you're splicing up individual textures. Sometimes they don't always align perfectly. Sometimes you might still have to navigate the semantics of the tile sheet versus just the overall straightforwardness of the operation. And so with that, now we've essentially got the entirety of what it means to store the board, at least in terms of it visually and also for persistence for right now. OK, I'm going to take a drink real quick.
Okay, copy that. Audio's coming down.
All right, so with that now, we've looked at how to think of tiles sort of as data. Right now, it's literally just a number. It's just a random number that we're effectively using to index into our sort of array, our table of quads. And we're going to put that aside for now. We've got our quads, we've got rectangles, we've got textures drawing, board state largely sort of figured out. But now we need to take on, I think, one of the bigger parts of this week's lecture, which is the idea of timers and things that are happening over time, or if it's happening after a certain period of time. And I want to just re-look at a couple of things. So in particular, I think to start with, I should say, the first time we looked at this was in Flappy Bird, when Flappy Bird had pipes that were moving from sort of right to left on the screen, and that was occurring on a timer. And I'm going to show sort of a naive approach to how we could do this ourselves. And let's go ahead and to do that, I'm going to go ahead and close all of these. There were a few things that we've seen, and we'll take a look again at those things as we're looking at all of these and how they apply to the game. So timer, we'll look at timer 0. And I'm just going to run timer 0 just to show it for now, to get started. It's very simple. It's just a timer, literally just a text string changing some number that's incrementing every second. And this was effectively what we were doing with the pipes in Flappy Bird, except they were moving, instead of a timer, a second going up every 2 seconds or so, we would have pipes that would be moving from right to left, or spawning to move, then move right to left. And then their position would change over time until they got to the end of the screen, and then they would despawn. And that's fine. It works in a simple sense, but it is a little bit cumbersome, especially when you think about, what if I have 10, 20, 30, 50 things that are all moving around on the screen, right? Let's take a look at how we're implementing it here in timer 0. So all we're doing is literally just, we know that we need to draw a second on the screen, and we know we need a timer to measure how much delta time has passed, so that we can eventually say, okay, a full second has passed, let's increment second, and let's wrap right back around to 0 accumulated milliseconds effectively, or fractional seconds. So here in update, we do indeed have the timers getting its DT increased. And then if second timer is greater than 1, in this case second timer meaning like number of seconds, then we'll increment current second, and then we'll just modulo by 1 to loop it back around to 0 point whatever something. And the result of this is that, sure, we have this looping timer. Every time 0, this number that's 0 is going to accumulate up to 1, it'll go back to 0, and then this will, over time track things perfectly the way that we want to. It's fine for now. But I would argue that it's not the most elegant or efficient way. It can be quite ugly, especially if we were to look at, for example, the idea of having maybe multiple timers that have different intervals, for example. So let's go ahead and open up timer 1. And I'm just going to run this. And we'll see that, OK, we've got different timers running now. We've got a timer running every second, every 2, every 4, every 3, and another every 2 seconds. And they're keeping in step fine. It's great. But let's look at how we actually implemented it with our current approach. It's not the most elegant solution in the world. There are, of course, ways to improve the way this is structured and organized and whatnot. That's essentially the point of what we're going to start looking at here. But you can see that this approach, even mentally, if we're just thinking about it, it can be a little bit cumbersome. We have all of these timers. We have all of these actual values that are getting adjusted and incremented. And it's just not a pleasure to deal with, especially in update. All of these have different times, different durations that they need to be kept track of. DT needs to apply to all of them. It's just not, it's not great. It's not a great approach. So what we can do is we'll take a look at timer 2, which is the clean way to do this. So I'm going to go ahead and clean way. It's always going to be subjective. But let's go ahead and open up timer 2. But before we do that, actually, let's talk about how we're going to do it. So there's a library in this ecosystem. You could get something similar to this, analogous to this, in many different environments. In particular, what we're going to be looking at is similar to a lot of what happens in the web world or the JavaScript world. But this library is called Knife, but you could even make something like this yourself if you wanted to. It's got a lot of really cool modules. We'll be looking at only a couple today and throughout the course of the term. It's got a lot of various things that are really neat, but timer in particular at the bottom is going to be our biggest one today. And also chain, we'll be looking at chain a bit. These will recur throughout the rest of the term. They are ubiquitously useful tools to use to make your games a lot more smooth, and also just conceptualizing time and things moving over time in a way that's not as manual or procedural. I think that's really the bigger takeaway that I want to emphasize. And so there are a couple of functions that we want to take a look at here. So timer.every, timer.after. And if we think about this, when we want to do something in our world, often when we think about transitions, for example, every 1 second I want to increment the counter or decrement the counter. We already saw that with the timer in the game. Or after 1 second, I want this thing to move over here. I don't want it to do it every second, but maybe something moves into a position, and then after 1 second, I want it to then move to another position. We did see that in the transition state of the game, which had the level text. It moved from the top to the middle, then from the middle to the bottom after about 1 second or so. And these two alone allow us to do so many different things based on time, based on thinking in terms of time and not having to manage time in a sort of unintuitive sense. And so that's what this library, in particular timer, allows us to do as part of the knife library. So let's go ahead and take a look at, before we go to that next part, we're going to use this to clean up our code. So we have manually managed timers up till now. I'm going to go ahead and transition over to timer 2. And I'm going to run it first. And you'll see it largely looks the same, except I've added an 8-second timer at the very bottom. We'll let it get to at least that point. But you can see they all operate in lockstep very cleanly. It's very similar to what we just saw. I'm going to go over back to timer 2. And the key difference here is that instead of doing all the things that we were doing previously, I can set a group of intervals. I can then set a group of counters. And then I can just iterate over all of those. So recall we had every 1 second, every 2 seconds, every 4 seconds. And then we have the counters that should map to those, the actual incremented numbers to show how many of those blocks of time have elapsed. Rather than keeping track of all of the delta time and updating them and then having all of that chaos of code, we can just use timer.every and then just say, OK, in a loop over that list of intervals and say every whatever that interval is. Notice I'm passing it an anonymous function. So it's basically saying, OK, it's making a contract that says, OK, after that thing happens or after that every increment of that period of time happening, I'm going to execute this block of code that you give me. This is, again, the anonymous function idea we looked at with state machines. Here it allows us to give it behavior that should happen at a certain point in time. It literally is just taking this in as if it were data like anything else, like a number or a string. And it keeps track of that. It holds a reference to it. It doesn't have to be declared anywhere. It doesn't have to be named anything. And once that interval has been passed, every time, I should say, it passes, it will perform this block of code. And we're aligning the interval with the counter here such that we then cleanly have everything getting updated in clean lockstep. And the best part about this, if you remember how big our update function was, is all we have to do now is just update timer. Timer.update dt, and it will manage all of these variables behind the scenes for us in terms of the dt and how much time has passed and whether we need to call the thing, and it stores the block of code. And it's very powerful. Here we're just using an example of a very simple, just incrementing some value, but you can put, because it's an anonymous function, you can put whatever code you want in there, and we'll see this used in multiple instances throughout this repo. But as you can see, we've gone down to 72 lines. If we were to open up timer 1, it's 100 lines, and I'm sure you could clean this up in some way to not be as, bulky. But just in terms of thinking, it's a lot easier to think in terms of like every X second I want to do this thing, or after X seconds I want to do this thing, than it is about thinking in terms of I have 6 timers that I want to update. And think about if you have not just timers and simple numbers, if you have positions of things moving around in space, or properties of things that need to get changed, or various, whatever you can imagine happening, and it gets very complicated very quickly, this allows us to solve that problem. So that's essentially what timers allow us to do. every X seconds or after X seconds we get to do stuff. I'll draw your attention again to where we can see this immediately in our source code. Just as a reminder, match 3, every 0.075 seconds approximately, those letters are changing. You can see after 1 second, the level 1 stayed there in the middle of the screen. And also the timer is going down 1 second. We don't have to have timers to manage these things anymore. And this allows us to do a lot of really cool things. This allows us to go into not only more visually interesting domains, but just smooth domains that feel more natural and organic. And allow us to do things like, for example, if you can imagine you're playing a game, a strategy game or something, and you want to move a unit between 2 squares. You know, you don't want to do it just instantly, discretely. Sometimes you want it to move between the squares. Things like that are very important. And that's another part of what we're going to be talking about today, which is also tweening, which is the next step. So I'm going to go ahead and transition here. So speaking of tweening, so that's sort of like the first step in terms of like time-based thinking is after a certain period of time, every amount of time, let this thing happen, do this thing. Don't make me think about the details about managing the time and moduloing back to 0 and doing all this stuff. Just let me say after every X do Y. But OK, that's fine. What if we want to move something smoothly between 2 positions or to do something between 2 values in a way that is continuous and not just instant? So I'm going to bring up match 3 again just to illustrate this. So in particular, notice that when I hit start, the transition from this state to the next. And also that operation there. So that level operation was a combination of ultimately the timer.after and then the tweening operation, which we're about to talk about. But we faded to white, and then we faded out from white into the next state. We had this sort of smooth transition between the two. And previously, in all of the lectures, we just instantly switched. But now we have the ability, or I posit that we will have the ability to do something a little bit more elegant in this way. And I'll illustrate that later concretely in the code base. But for right now, let's actually understand how tweening works. I'm going to go ahead and open up tween 0. The tween just being like between 2 values. Let's go ahead. I'm going to close the others here. Let's just run this. And you'll see that we have sort of the Flappy Bird graphic from previously moving from left to right. Now, if we were to think about, OK, how do we move something with over the space of 2 seconds from one area to the next? I mean, sort of previously we did that in a way with the pipes, although we didn't explicitly know that they should move between right to left over a certain period of time. They just had a velocity. Well, every 2 seconds we spawned a pipe, and then we approximated somewhere in there that over a certain period of seconds, that'll be how many pipes move from right to left. But here, you know, up till now, we've essentially just been letting things move around through physics, or let gravity apply, you know, positive y velocity to the bird. Here, we're actually deciding, OK, I want this bird to move from the left of the screen to the right of the screen over 2 seconds, concretely. We don't really have a way to solve that yet. So I posit there's a way to do it sort of naively and crudely. We could essentially say, OK, the bird's x position is going to start at 0. And we know that we want its x position to end at essentially virtual width minus its width, because then that'll account for its width touching just against the wall. And then we can say, OK, I'm going to maybe multiply that end value. I want its x value to eventually be that value. So I can essentially just multiply some value by 1, or I can try to get some coefficient to be the value 1 against that value and set its x to that. So I can essentially say, OK, if it's going to be 2 seconds, we need to add up 2 seconds worth of delta time. And then once that ratio becomes 1, delta time over 2 becomes 1, multiplied by that end destination, we will have reached that point. And assuming that we're interpolating it, we're doing it every frame, we're adding that every frame, we'll see it move from left to right. So I'm going to go ahead down here. We'll see we set it at just 0 to start with. The y is irrelevant for this example. We have a timer. We're doing this manually here. We're not tweening ourselves. And we'll say that there's a move duration. We've defined this to be 2 up here, 2 seconds. So again, another manual operation. And then we're going to set the x of the bird that we're going to draw to the lower of, and this is going to clamp it so it can't get any farther than the right side of the screen, end x being that destination that we talked about, times timer over move duration, meaning that timer, we want that to be 2 seconds. We want it to move over 2 seconds. This is going to start at 0 and effectively gradually move towards 1 as this approaches 2 seconds worth of time, at which point this will essentially be multiplying by 1, and we will have arrived at end x. So this is a very crude sort of linear interpolation, assuming that we start at 0 here, which we'll see a more robust version of that coming forth, which is fine. This works. This works when you assume that you start from 0, which isn't going to apply to the majority of cases probably, but it gives us a starting point and allows us to do interpolation over a set period of time. We know that we can set this to whatever we want to. We can set move duration to 4 seconds if we want and run it, and it's going to take 4 seconds instead of 2 seconds. And that number at the very top is just showing a little bit of overlap when delta time is just going to slightly go over 4 between frames, and that's fine. That's expected. But you can see it works. But it is a little bit heavy-handed still. We're dealing with timers. So we clearly have some iteration. We have some refinement we can do. Let's improve it a little bit. I'm going to go over to tween 1. And I'm just go ahead and run this to start with so we see what's going on. You can see we've got a lot more birds, and they're sort of all moving at different rates, which is good. We've got, and it's 10 seconds capped. I'm running this at 24 frames per second. But we have essentially now 100, I think, or so birds that are all spawning. They're all just tables with a rate that they're preserving and some change over time, which is cool. It's fine. It's great. It showcases that we have some way to scale this at least. I'm going to go ahead and show here we're inserting into birds 1 over 100 at the start of main. We start them all at 0 on the x. We start them at just some random y value so we can actually see them all sort of moving with each other. And then we set a rate for them as well. So this rate will allow them to all independently move. And we're going to set that to be some sort of random value between 1 and the max. Some sort of value between point something and the end of whatever the 10-second value is. So it'll be between 10 seconds and 0 point. It'll have some sort of fractional amount in there. We have to do this. Math.random will give you between 0 and 1 floating point. And the reason we're doing this is because if you were to set it just to be math.random as an integer, it will only give you integerial numbers. And so this allows us to have a fractional value between 0 and whatever that end value is, fractionally as well. So it'll add point, whatever it could be, 0.5, 0.2, to 1 through 9, so that we end up getting between 0 and 9.99999. Or actually, well, technically it's from 0 to 1, so we could get 10. Now, this is fine. And then ultimately, we have a timer, like some sort of global timer. And then we're going to, in our update, we're still doing things manually here. We have this timer that's updating. And then we're going to take the timer, which is acting as this sort of like global clock for all of our objects. And we're going to do the same interpolation that we did last time, except now we're using the bird's internally stored rate to determine whether that ratio has reached 1. And it's fine, it works, but there are issues with it. Like we have this global timer that now is being checked against everything. If we have new things that start after the timer has already started, there's going to be difficulty coordinating that. It's not going to scale very well. We're still manually thinking about things in terms of timers. So there's a better way, I posit, than any of these approaches, which is the timer.tween way. And so timer.tween is cool. It's essentially the same kind of function as timer.every, timer.after. In this case, it's going to take some duration and then a definition. And this definition is going to be, OK, I have some period of time that I want some operation to occur, some interpolation to occur. What do I want to interpolate? And what's cool is, as we'll see in a second, Lua allows you to define table keys using tables. So we can say, OK, I want this object to interpolate its certain fields over this certain period of time. And this not only gives us a nice sort of syntax for describing this operation, but flexibility. We were just doing position there, and it had an interpolation sort of expression there, which was just based on the x value. But what if we wanted to do other things, other fields? We'll see how that works in just a second here. But this essentially is going to be the way that we accomplish exactly what I'm talking about without having to worry in terms of this global timer and this clumsy sort of way of thinking about time manually, which we want to get out of the habit of doing. So I'm going to go ahead and go to tween2, rather. Let's run this, see what it looks like. You'll see we have a lot of birds. That looks like more than 100 birds. And not only are they all moving from right to left, as they were previously, but they also are interpolating in another attribute within their table definition, their object, if you want to think of it that way, and that is their opacity. They started off opaque, or they started off transparent, and gradually, as they moved from right to left or left to right, they became fully opaque. So, and as we'll see here, I'm going to go ahead and open up this code. We're using knife.timer, which also, if I hadn't alluded to that previously, this will be in all the repos, all the examples. We're just importing it as an object. It's just a library, just like push is, just like classes that we've used so far. And this will be in every example. We're going to go ahead and see all of the, we do 1,000 birds. That's a lot of birds. But we're also setting the rate, just like we did last time. They each have a rate still. We want them all to move at their own speed and keep track of it. Also, an opacity that starts at 0. And here is the function in question that's important, which is timer.tween. So for every bird that we are defining in this sort of list of this table of birds, and we're just using a very simple, not even using class, we're just using a table to sort of represent a simple class, simple object, inline. We're going to go ahead and call over each bird's rate. So we're iterating over every bird, all 1,000 birds. We're setting its, using its rate, we're going to define a tween. We're going to set timer to tween that value, which is essentially saying here, manage this operation for us. Again, this is all happening in load, so this is only happening once. This is happening up front. We don't have to then worry about it too much. And then notice again, we're passing the bird in as a key. It's going to take a table here. That's what this is. So the bird, Lua allows you to use tables as keys. And this is one of the benefits of it is you can define with your library sort of this cool, these sort of DSLs of a sort to sort of express ideas. But here we're saying, I want to take the bird and interpolate its x to end x and its opacity to 255. So whatever it is at this moment in time, it's going to perform an interpolation on that for us. And we can pass in any number of fields we want to, assuming that we assign assuming that that field exists within the bird, and it's going to have some sort of end, as the left-hand side rather exists already, and this end value is an expression that is interpretable or is derivable for right now. What this ends up being is that now, okay, every bird is going to be, a reference to it is going to exist as a key. Timer.tween is going to do the equivalent of that interpolation, but we are not going to have to manage it ourselves anymore. Now it's just literally timer.update dt. It's that simple. And now we have scalability for any number of fields that we care about. I'll just run it again just because it's fun to look at. But not only do we get x, but we also get opacity for free and any other attribute. And this is very important for any of the future lectures, including today's lecture. This tweening, we saw multiple instances of it. Let me remind people of that. If we look at match 3, let me just run it. We'll see that opacity of that full white to transparent of that rectangle is a tween operation. So is the position of the top to the middle to the bottom. And then if we move any two tiles together, that's a tween. It happens very quickly, but those two tiles are tweened to be opposite, in this case in the y-axis. We can do the same thing between these two right here. And then if I solve a match, all of those tiles, every single one of those tiles that came from the top had this Y value tweened to be where it needs to be now in the grid. So those are a lot of the main features, a lot of the main ideas that we need to use to expand our repertoire, so to speak. The last big piece that Timer gives us, or Knife, the library gives us, is this idea of chaining. And chaining is cool because it allows us to essentially think of operations in sequence throughout time, which right now it's kind of difficult. So if I want to think about, okay, well, the birds, yeah, they all move in one direction. The birds will move from right to left or left to right, and then their opacity changes. But what if we want some character on the battlefield or whatnot to move around in a series of steps and to have that be smooth? Or we want some thing to move around on the screen in different positions, almost like I guess I'm envisioning the old screensavers that would do something like that. Well, let's go ahead and run chain 0. I'm going to go ahead and show what this looks like. So we have an implementation of this idea. We can see that the bird is moving sort of from left to right, then it moves from top to bottom, then it moves from bottom right to the left, and then it moves from the bottom left to the top left, back in its original position. Now, we could do an approach of that is sort of naive in a similar sense that we've done so far, in that we could say, okay, I have this set of destinations. I know that the bird's going to need to move left, it's going to need to move here to this x and y, it's going to need to move to this x and y, then to this x and y, then to this x and y. Each destination should probably be marked as being reached or not, because we're going to iterate through them in sequence and ultimately determine, okay, I need to interpolate its position between these two values, right? So if we come down here to update, we're not using Timer at all here. This is just our own in-house implementation of this idea. But we can iterate over all of the pairs in that destination that we looked at and say, okay, if it wasn't reached, we'll just set our x and y to be the interpolated sort of next value of whatever the destination is relative to our base. And so far, thus far, we've only been interpolating from 0 to 255 effectively. With timer.tween, we could set the start point and end point however we want to. It's fine. In this particular example, this is also to illustrate a more robust way to define the interpolation algorithm, which is that your x should be some sort of constant value that you start from, that you then interpolate towards your destination value from. We've been starting it at 0 implicitly. You can start this at 1. You can start this whatever you want. As long as it's different from your ending value, the interpolation math will work out such that if you were to subtract the destination value from your actual base value and then multiply the timer over movement in order to eventually make that coefficient be 1, by adding that difference to wherever you are right now or wherever you were at the base of when the interpolation was figured out, you will eventually arrive there once x seconds have passed by. So this is essentially kind of a way we were implementing the manual timer approach previously when we were looking at tweening. But you can see here, once it reaches movement time, cool, we'll mark it as reached. Cool, we went through destination 1. Cool, we reached that. Okay, destination 2 is not reached. Okay, well, we'll move down there now. Okay, cool. Setting our base x and y to be whatever that last destination was, which is what we do right here, because the interpolation assumes a base. It assumes this x and y here. Any value that you interpolate needs a base in order for the math to work out, such that you go from the one position to the other over that span of time. You essentially create that line segment between the two destinations. So we have to set our base and base x and base y to our destination, and then reset our timer, and then we can rinse and repeat this idea over and over again. But what kind of isn't great about this approach is that it's quite cumbersome. It's not very scalable again. We're thinking in terms of, the actual interpolation. We're not thinking in terms of like, okay, the bird is going to move here, and then after that it's going to move here, then after that it's going to move there, then after that it's going to move there, in this sort of linear way of thinking about time. The destinations are described linearly in the sense that they are structured linearly, but the way that it's implemented and described and shown, I would say, isn't quite the mental model that I like to think about this kind of stuff, and I think most people prefer to think about this kind of stuff. So if instead we were to go to chain 1, which is the better way to do this, in my opinion, using Knife's chain functionality, which is essentially this finish function here. So timer calls it chain. That's just the object that they define as these finish functions that result off of these tween operations. You can apply it to any function that you want to. It can apply to an every. I think it might have even, did I have a slide about it? I did. So timer finish, which is their idea of chaining things together. So you can call this after any timer function, as shown here, whether it's after a tween, after an every. It's just the idea of once one thing happens, we should transition to doing this other thing right after that. And we can describe it, therefore, in linear time. Or rather, we can describe it in linear code and not have to think about it in this sort of disjointed way of thinking about interpolations and managing time, doing all these things that are rather cumbersome and rather sort of separate from the problem at hand. And so with this, we'll be able to begin looking at our idea of moving the bird through space in a quite straightforward way. If we transition back to here, we'll see we have our initial bird's fields here, just a very simple object of x, y opacity. We're setting the opacity at 255 to start with. And then now what we're doing, you'll see that there's this odd sort of like nested callback kind of code here, which this is a common pattern, especially in web, especially in historical web code. This idea of a promise of this thing that is going to happen after some period of time happens. You're promised to get this value back for this, or for this callback function to call to do something for you. And that's essentially what this is, only that's just called with different words here. In the web, you might see .then. Here, we're going to see :finish. So after this thing is finished, this timed operation is finished, this movement time has the Flappy Bird moving to virtual width minus its width, so the bird's width itself, so moving all the way to the right side of the screen. We're also changing the opacity. This is the same syntax, for this is the tween function which we looked at. Once it's finished, it's going to call this anonymous function, which is going to itself have a timer.tween within it, which we can then, over the same movement time, pass in the same Flappy with different values, x equal to virtual width minus Flappy sprite.getWidth, so it's going to still be at the right side, but then we're going to move down to the bottom of the screen. We're going to say y gets virtual height minus its height, and then we're going to, in this case, we set its opacity to 0 for the first movement. We're going to set it back to 255 when it moves down, and then we're going to repeat that exact same operation essentially the rest of the way to get the exact same code that we saw previously, only again, all we have in our update is just this timer.update. I'll run this, and you can see not only are we interpolating over time this set of individual steps, our bird moving, but it's also sort of phasing in and out of existence, kind of like a ghost in Mario or something, which is cool because now we can just think in terms of the actual linear nature of what we're trying to conceptualize over time. I don't want to have to worry about managing timers and doing all this sort of manual work of thinking and creating a data structure to represent these movements. Let me just call these blocks of code in sequence. And you can, if up to your choice, to your taste, you could choose to maybe not have them all be at this level of indentation. You could move them back and then just kind of have it like this, ultimately, and then sort of do the same thing here, if you prefer. And then you're sort of really looking at it in terms of just very linearly and not thinking in terms of the callback actually happening. But timer is going to essentially just store this function, and then just finish is going to call once its time operation finishes for each of these, and just trigger that callback function. And you can call another timer.tween or timer.whatever you want, just like you could increment the counters that we looked at previously when we did timer.every and timer.after, kind of a similar idea. And so with this idea, now we can represent essentially almost anything over time. On finish for any particular thing, we can just say, hey, move this thing here, move this thing here, perform this calculation. After I swap two tiles, calculate, was there a match? And then, after the tween is finished, and then perform the actual moving of the tiles. And then after that, set the cursor to be some color or do something else. And this is one of the bigger pieces of this lecture, is this ability of thinking about time through your game and being able to do smoother animations and transitions between states, but also just between objects interacting within your states. Cool. All right. Glass of water, or drink of water. Cool. So with that, we've looked at time, we looked at managing time, transitions, movement, tweening, and timers particularly, and also a look at anonymous functions, again, which is all the more going to be prevalent throughout the rest of the code. But I think sort of the big elephant in the room, we started off the lecture with the grid. We started out laying out the tiles and persisting them. We can move things around, but we need to actually be able to start interacting with the grid before we can really be productive in match 3. And so let's go ahead and start with swap 0, which is going to be our very initial example to illustrate. And again, a reminder, this is what we're dealing with the tiles. We just have a list of essentially quads defined left to right, top to bottom. These are all getting IDs effectively and we're indexing into that quad table that we're creating. And with that, we can essentially start to compare two tiles and move them around as well. So I'm going to go ahead and go back here to the code. Let's go ahead and close out all of these examples that were there before. And let's go over to match or swap 0. Let's run this. So this is largely what we had before, except now it's not filling up the entirety of the screen. This is actually in line with what we expect for the game itself. It's an 8x8 grid of tiles. These are all just random, and they're persistent. And with that, we can effectively begin to, if we want, we could draw a cursor. We start moving the cursor around, and then we can start thinking about, OK, we have this grid. What if I want to move 2 blocks around? Actually swap them, right? The grid has to actually be interactive so that we can then apply the check in order for this to be match 3, properly match 3. I'm going to go ahead and let's just take a look at what we're doing here real quick just to establish the scene. Nothing too much that we haven't seen already. We have a generate board function, which is handling the actual board generation. Everything else is largely pretty germane. We have a draw board function, which takes an offset on the x and the y so that we can center it appropriately once we have it drawn. It's not just drawing at the top left anymore. It's actually within the confines of the screen. So generate board here, we saw this before. All this is doing is just that 2D array. It's going to go through row by row, column by column within each row, insert within those column, into those row tables rather, these IDs that end up actually being what we index into our quads table to draw the quad at. So overall pretty simple right now. The only difference is that rather than the ID just being the only thing we're storing, we're also storing everything as within a table right here. So we have an actual full table within which the tile itself is preserving that ID, and then we have an x and a y coordinate because we do need to draw these tiles. And as some folks might be able to predict, when we do things like tweening, those tiles are going to have some sort of index into this array, but they're going to need those x and y values that actually move left and right, or top to bottom as they're swapped. Those are going to have to interpolate, and so they have to actually be a stored value within this object that we can move around. So with that, and again, just for illustration too, just to bring home the point, this is an illustration. This is just a code, rough mock-up of what in memory this would look like in a simple form, previously especially. Right now they're tables they have essentially that number behind a tile field, but you can envision our grid as essentially this. It's essentially just a array of arrays of numbers that are sort of elegantly wrapped in a table, which also will carry with it color and variety metadata, and then the x and the y that we can then interpolate. But this is essentially the mental model for which we can navigate looking at our grid of tiles, and this transcends into all other domains within which we'll look at tile-based anything. In particular, next week when we look at Mario, this is essentially the foundation of that lecture as well. Let's go to swap 1 now, and here we're just going to illustrate a swap that doesn't actually have much of a visual sort of thing going for it, but illustrates what it means to swap the tiles. I'm going to go ahead and open up swap 1. Not going to be smooth, not going to be animated, not going to be fancy, but I can move this cursor around. And if I want to move, for example, this tile here, I can just do it. And it's instant. But it's depending on your preferences, maybe that's OK. It's certainly not, I think, what most people expect, especially playing games like Candy Crush or Bejeweled. There's some sort of animation that should happen. But we have the gist behind having this grid of tiles, this grid of numbers that we're essentially able to move these numbers around with. So let's go ahead and transition back to the code itself. Now, we have our board as usual. We have whether we are currently highlighting a tile, meaning that we are ready to swap a tile. So recall, actually, if we are ready to swap a tile, notice that there's a rectangle, a highlighted rectangle actually applied to whatever we just chose there. We're not really doing any bounds checking currently in this example, so we could just swap these two, for example, if we wanted to, and it's totally legal in this code. This is not how the main distro works, but just to illustrate. But we do have a highlighted rectangle to illustrate, okay, this is what you chose, and then here's where you're going to swap. And so there's a reference that has to be made to that. So that's what we do here. We have a highlighted tile, and then the actual y, x and y will preserve that when we are highlighting it, but we don't need to. This isn't being used until we actually have clicked enter and are highlighting the tile. In this case, we do also want to be able to select or hovering over tiles is going to be the indicator for our little red cursor to show, okay, we're moving around, we need some way to show which tile we want to select, which actual tile we want to highlight and then swap. So that's what that's for. Here in love.keyPressed, if we end up pressing up, down, left, or right, we're going to clamp our x and y values by the board's size, which is what we're doing here. And then after that, we can press enter or return and then actually determine, okay, if we pressed enter once, then we've highlighted something, and we should just either highlight it or unhighlight it, or rather, we should either perform the swap if it's on a different tile, or we should unhighlight that tile. So we haven't highlighted anything. Let's do the highlight, and then we'll end up just swapping them. So here we go. It's just ultimately a pretty simple, like defining temp x and y for whichever, pick one of the two tiles, swap the two by setting the other tile to be the xy of the other tile, and then with the temp tile that you've chosen, set the other tile to be the temp x and y. So it's a relatively simple swap operation here. And then once that's done, we can also swap them in the board as well, which will allow the board to sort of keep a persistent, rather the board at grid Y and grid X will be set to the actual instances of those tiles. We have to actually swap the individual tiles to do that. But then once the coordinates and the grid position are swapped, we can then unhighlight whatever our last tile was selected. Sorry, that was horribly worded. I need to reword that. I was stammering over myself. So we could press enter or return, and what that'll allow us to do is if we are highlighted already on a tile, it will perform the actual swap operation. It'll do the check, and then it'll actually swap the tiles. If we're not highlighted, well, then we haven't got an initial tile to swap, so it's not going to do that. It's going to actually highlight whatever tile we want to by setting the highlighted X and Y to be whatever that tile's grid X and Y are, and then setting highlighted tile to true. So if in the event that we've already got the highlighted tile, what we're going to want to do is we're going to want to swap them by getting a reference to both of the tiles here. So, and then at that point, we can just essentially swap their information by getting a temp X and temp Y to be equal to tile 2. So that'll just preserve essentially its X, Y, and grid X and grid Y. We're going to save them both as sets of variables. At which point, then we can swap their places in the board. And then we can do the sort of like classic swap operation where you have a temp variable, you have in this case we have an XY, a grid X and a grid Y. So we're going to take whatever the temp variables were and give them to tile 1 because we took them from tile 2. But tile 2, we're just going to then take whatever tile 1 currently has before we do that. And then therefore they're going to have swapped data, and then they'll be able to unhighlight them rather, and then that'll be it. Our selected tile is going to be tile 2, which is where we end up on. We're going to be still at tile 2 for our cursor. And there's some folks might say, you know, a few magic numbers in here, 1, 8, various numbers like this. This whole game was largely designed around a consistent aesthetic and arrangement of tiles. But if you wanted things to be a little bit more robust, and this transcends also from here into the Match 3 distro proper, but you could set 8, for example, to be like grid width or grid height or grid size in this case. And then you could tweak that if you wanted to play a game with, you know, 4, 5, 6, 7, 8 sized dimensions on your X and Y. But in this case, things are very specifically tailored for a few specific numbers, so that's why you'll see numbers that way. So that's essentially how you can swap the variables. They're essentially just like taking the metadata of those two tiles and swapping them, literally just like changing the X, Y, and the grid X and the grid Y, and then that's it. And then we can draw it here. We saw that before. The generate board's still the same, and that's pretty much it. Here we're also drawing the red rectangle that's going to go around our cursor. Here, that's what this is. This set line width to 4 is just like the stroke size, essentially, of that rectangle. And then we just draw it over whatever our selected tile is. And then we also have this offset we're using to draw again, the board to a different, it's right here, this offset X and Y, so that we can draw it centered on the screen. This is applying to the cursor as well, so that the cursor gets moved around. It's not drawn relative necessarily to 0 on the top left of the screen, it's getting offset. And then we set you might see this as well a few times, this set color 1, 1, 1, 1. If I didn't allude to that last time, that's because when you set color in Love 2D, this is sort of like a global color. So if you forget to do this and you see weird greens and blues and other colors like that, just make sure you set your color back to 1, 1, 1, 1, which is pure RGB white color at full opacity. Make sure to set it to that just so that whatever the next thing you draw isn't preserving, for example, this red color, which would be the case if you were to like not set that back to full white. So that's the static swap, so just essentially a data swap. But you know, if we are looking at this world of timers and tween operations and whatnot, well, we can do a better job if we were to do a tween-based swap instead. And really, it's essentially going to be the same thing, except now instead of hard setting the X and the Y between the grid, or rather the grid X, or rather, yeah, their X and Y, not their grid X and grid Y. Those will stay small and discrete, but their X and Y values will actually be tweenable, right, to sort of spoil it, I suppose. Right now, we're just hard swapping them, but if we were to tween them back and forth to whatever the other tile's value was, well, we might be able to achieve a slightly better effect. So I'm going to go ahead and bring this over to swap 2. If we run this, so it's largely the same, except now, if I were to select this tile here, you'll notice that they swapped smoothly over time. It wasn't just an instant sort of transition that happened. we've decided on some amount of time, point whatever seconds, 0.0 something seconds, or maybe 0.2 seconds. And what this is going to do is the x and the y, rather than being just like instantly, okay, this tile was this tile's x and y, and now this tile was this tile's x and y, it'll be some sort of like, let's smoothly interpolate. And then that gives us whatever this tweening effect is. We do it again here. You'll see it just happens smoothly. Same thing that happens when the tiles come down from the top of the screen, or when tiles that are currently inline get a space below them because of a match. They come down, they tween themselves down, rather than just hard setting their position to be that new value. They'll move in the actual table where they're stored. The actual get swapped in the table, but they preserve a reference to their actual x and y position, so that timer.tween can then like smoothly put it into the right place effectively. And we'll go ahead and we'll just look at main here. If we come down to our love.keyPress, there's all the same stuff kind of that we saw previously, except rather than the hard transition to x and y, or their hard x and y is getting swapped here in the code, notice that now we're setting a timer.tween. No finish or anything like that, just a simple tween. But here we're just passing in tile 2, and we're saying its x should be equal whatever tile1.x is and whatever tile1.y's is. And then tile 1 is just going to essentially get whatever the temps is. Its x will be whatever the temp x is, and the y will be whatever the temp y is. And as a result, these are going to now, thanks to timer, have a nice transition between them, and things look visually a lot smoother. And it's just kind of easier once you have a lot of these things going on to not have to manage them quite as much, as meticulously. It's still unavoidable at a certain point. There are certain things you're going to have to manage, grid positions being discrete for checks, and then the actual positions of the x and y moving around independently of that. But at least we've saved ourselves a little bit in some sense, but also we've gained a lot in terms of visual smoothness and fluidity. So that's the extent of the sort of examples that we'll look at before we end up taking a look at some of the aspects of the code that are relevant for the problem set. We're going to look now at matches. So matches, this is the most fundamental aspect of the lecture itself, or probably shouldn't say that necessarily, but it is the underpinning of what makes match 3 work. Certainly right now we can swap all we want to. Things aren't really going to work. We can't have a way of gauging whether we've won the game or cleared a level or whatnot. This is the last big piece, is how do we determine that we have a match? And then once we have a match, how do we determine, okay, well, we're going to have to take tiles out. How do we put them back? How do we get new tiles? How do we shift tiles? So matches are relatively easy in that essentially if we have just a grid of tiles here, we can think of any match as being just 3 or more contiguous tiles of the same color. We can define this however we want to. For this example, we're going to say it's just the same color, 3 in a row in either the x-axis or the y-axis, not diagonals, but just orthogonal axes matches in a row. Those will be a match. So if we start at the very top, and let's assume that we're going to look at every row first. We have to first calculate, okay, we're going to have to take care of the x-axis. We need to check all horizontal matches. Then we're going to need to do all of that again, but oppositely 90 degrees on the y-axis to calculate vertical matches. But let's just start with horizontal matches. So we'll start here. And then we're just going to essentially say, okay, we're at this first row. We'll check this block. This is khaki color. Okay, cool. We'll check the next color. Okay, it's red, so it's a different color than this last one. So okay, we're not going to preserve any idea of a match. That's fine. Okay, next one's blue. Same thing. Okay, it's not pink. It's not going to be the same color. Okay, what about the next tile? Okay, it's blue. Okay, so we're in it. We're currently in a match. We don't need to reset the color. And then, oh, okay, we found a match here. This is 3 in a row. And we can keep going until we get to different color, in the case that we get 4 colors. But here we've also reached the end of the row. When we reach the end of the row, we're also going to check, okay, because we're at the end, we can't check whether the next color is different because there is no next color. So we're going to basically say, okay, do we have at least 3? Let's return the match. We're going to do the same thing now for the next row, just going one by one. We're at blue. Okay, red's not blue, so it's not a match. Green's not red, or pink, so it's not a match. Yellow's not green, so it's not a match. But then we got 2 yellow, but now we're at the end of the row, and it's only 2. It's not 3, so it's not a match. It doesn't count. We'll do the same thing, kind of going through. We're always just checking, okay, is this color the same as the last color? If it was, preserve that, else the new color is whatever this current color on this tile is. Do the same thing here. Okay, we got 2, but it's not a match. And then here, gray is not khaki, but gray is gray, gray is gray. That's a match. And then as soon as we hit purple, we determine that's a match and we save it. We'll do the same thing. We're going to go vertically. In this case, we're just essentially crawling through the rows now. Y is incrementing. We're doing the same check. Once we get to the bottom of the grid, we know, okay, no matches here. Okay, oh, we got 2 in a row. We got 3 in a row. Cool. That's a match. As soon as we know that we've gotten to the gray one, we can say the match is done with. It's not a 4-tile match or anything like that. We got 2 here, but again, we're at the end of the row or end of the column, so it's not a match. And then we're just going to loop through this whole process one more time, going through every single column. And then here we got our last match, just 3 in a row. At the very end, kind of the same thing. At the very end, check. Are we at the end? We can't check the next color. So this is a match because we're storing in state in some sort of loop. We've got 3 contiguous tiles. And then once we're done with all of that, we can essentially say, okay, we've got 4 matches in this particular instance. And we can represent them as just sort of, we could choose to represent them however we want to. We can say, okay, these will just become 4 tables that store these tiles. And then we'll just essentially say, okay, let's just get rid of them. Cool. So those are going to be empty spaces now in the table. We're going to have nil values here. Now the next step of that, obviously, we can't just leave it like this. We're going to have to say, okay, well, what next? Now we need to, first, before we even generate new tiles, we need to probably let gravity do its thing and say, okay, let's bring all these tiles down such that tiles can come in from the top then and fill in these gaps that exist. So what we'll do is we can essentially just think of this in terms of from the bottom up. We'll say, okay, is there a hole? Like if I go from the bottom to the top, are there any gaps such that there's an empty space below a tile? And we could do that by just starting at y equals the bottom. We'll just go up. Okay, this was solid, cool, solid, no problem, solid, no problem, solid, no problem. Nothing needed to be shifted. We'll go to the next column over, and it'll be on the x-axis. So we'll see immediately we have a space where there should be a tile. So this will be a nil index into our table. And so we can say, okay, I need to find whatever the next tile is vertically, and that's going to need to come down to wherever this space is. So we'll just go up a tile. We find it right away. And so we'll just say, okay, now that we found it, let's just put it right back to where the space was. Cool. And then we can say, let's do that same exact operation starting up above, the tile that we just placed down here. And so we find a space immediately, and we're going to do the same logic. We're going to say, okay, I found a space. I need to find a tile to replace. So it's going to go up. It's going to go up again. It's going to go up again, but it's going to reach the top, and it's going to say, oh, there are no tiles. So actually, okay, we don't need to put any bricks down to the bottom where we found that first space. We can just end this iteration of the loop and go on to the next column, which we'll do here. So right out the gate, we find a space. So we'll do the same thing. We'll go up. Okay, let's replace we'll put this tile down where we've had the space. Cool. We'll go up. Oh, another space. Okay, let's do the same thing. Okay, tile comes down, go up. Tile comes down, go up, and then we eventually get to the ceiling, quote unquote, of our grid where there are no spaces to fill in, there are no tiles to fill the spaces, but we have effectively shifted these down. And then we can do the same thing again for the next column, and then the next column. It's all the same logic. Look for a space, look for the highest or the lowest tile to then fall down, match that space, and then repeat until you effectively go all the way up to the top of the grid, which is the ceiling in the grid. And then once that's finished, well, okay, we cleared out all the matches as the first step. We then applied gravity to the tiles that existed already. And now what we need to do is fill in the spaces that now exist. There will always be spaces at the top of the board that need to be populated with tiles. So we can essentially do kind of an inverse of what we just did, in that we're going to start from the top in each of these rows, but we're going to just like count down how many spaces we get to before we reach the bottom. And in the case of a full tile here, it'll just be none, so we won't have to generate any tiles. So if I go ahead and start here, well, we'll assume, I guess, that we don't have to here, but essentially we would look here and say, oh, okay, it's 0, there's a tile here already, 0 tiles need to be filled in. But we'll go here and we'll say, okay, there's a space here, and then, okay, another space here. We're taking y at this column, and we're essentially saying, okay, y gets 1, there's a space, 2, there's a space. Okay, that's 2 tiles. 3 spaces, 4 spaces, just checking for nil in our board, and then finally a tile. So it's going to stop generating knowing that it needs to generate a tile for this column here, and then it's going to move over to the next. Okay, 1 space, 2 space, 1 space, 2 space, and then 4 spaces here. And then what that's going to do is it's going to say, okay, I need 4 batches effectively of tiles, or you could think of it in terms of individual tiles. In the distro, we think of it in terms of individual groupings of tiles for that row or for that column. And so what we'll do is we'll say, okay, we're just going to essentially tween in a bunch of tiles to fill in those gaps. We'll populate them. We'll put in the tiles with their grid X and grid Y. We'll set all of their actual X and Y to be some number above the ceiling. And then by just performing a Y interpolation, a timer.tween, onto their value, we get the effect of effectively a slide in from the top of all of the tiles that match up to the spaces that were left in our board state. And now all of the board is back into a relatively good shape. Things are fine, unless you have matches again, in which case now is the time that you would want to check for matches and then repeat this process. People that have played Bejeweled and Candy Crush and these kinds of games know that the most fun that you probably have when you play a game like this is when you just like get chain after chain of matches in a row and the board is exploding and doing all this crazy stuff. But that's effectively what we would do here until the board is in this sort of stable state of there are no matches left. So we no longer have to do any replacement, any checks for anything. The user is back again allowed to move their cursor around and try to swap tiles to affect a match. And so let's go ahead now and take a few minutes to see how these concepts apply to the code in the actual distribution. So I'm going to go over to the code here. We haven't looked terribly closely at the code in the course. It's in the distro itself for the week, but folks might notice it's slightly less dense than the breakout code in that it doesn't have quite as many bells and whistles. So we'll be able to focus, I think, and narrow in on some of the ideas a little bit more. But it is still functionally a full game in the sense that you can go through the full process of it. But we have elected not to do like high scores and various things like that, just to focus in on what was relevant for the week. So I'm going to go ahead now and look at a couple of these files. So I'm going to get rid of this main.lua. So board is important, tile is important, and then some of the states are important that we want to look at. Now, the tile is very simple. Tile is just it's going to have a grid X, a grid Y. It's going to have a regular X and a regular Y for interpolation, for movement. And then it's going to have its color and variety. And remember, when we talked about color is essentially the way that we are differentiating between tiles and allowing them to be compared for matches. And that's the field that we care about most for that purpose. And then it's a lot of the same stuff that we've seen previously. We're indexing into a frame array to draw the actual texture and just get whatever that ID is for the color. We have a utility function that's actually splitting the tiles up rather than it being a contiguous set of just a unidimensional array of tile rectangles. What we have is a function that is actually creating a 2D array off of, so we have our frames sort of table, which is divided into multiple different kinds of frames by convention. In this particular game's example, we're not going to have a lot of other types of categories of frames that we care about, but this will be relevant for other lectures. But this 2D array here is actually dividing things into color and variety. So if we go ahead and look at, for example, in util, generate tile quads is a build-up of generate quads, or it's essentially an extension of the idea, whereas instead of going through the entire spreadsheet or the entire sprite sheet based on the unit of whatever the size of the tile is and creating one table, we're going to go ahead and recall the texture in this particular example. If I just pull it up here, is actually split up. The rows are split up into 2 groups of 6. So we have 6 khaki, 6 magenta-ish, 6 like whatever green this is, and then 6 pink, and then 6 darker green, 6 red. And that's essentially all that this does, or all this pays attention to, is the fact that we can twice within each loop iteration for each row, we can essentially say from 1 to 6, and then grab whatever the tile is within that group, offsetting x, and then do the same thing, essentially doing it twice will allow us to split things up into 2. Yeah?
In this particular tile set, are the shapes on the tiles meant to be distractions from the colors?
The tiles, the shapes themselves are not so much meant to be distractions as they are meant to, in my mind, it was probably relatively ambiguous based on what the designer of the sprite sheet initially went for, but I interpret it as a way to have a higher value on that color, so that you can imagine if you started off all of these, they kind of initially have no design on them, but you could imagine having, for example, if you chose this star to be some sort of special tile that you then add a highlight to, or a particle effect or something, or this X, maybe you tint it some color, or you do something with it to designate it as being a bad color, or you just treat all of these as different values that are slightly higher than regular flat color. I see them as variants that can either be point multipliers or some sort of feature for the gameplay, a punishment, a benefit. The assignment itself is to create a tile such that if you were to match it, some variant, some shiny variant that will destroy an entire row in addition to other aspects of the problem set. And you could designate that via some particle effect or through maybe the star in addition to the particle effect. There's really a lot of options, I think. But the overall goal probably, if I had to guess, would be that these were probably point multipliers or feature multipliers or some other variant thereof. But essentially what this variant of generate quads is doing is iterating over each row, creating a row sheet, and then rather a half row sheet, which then gets populated with just the colors, just the 6 colors, 6 color block at a time, all the way through the sprite sheet, which allows us then to do what we see here, where we can index into the tile sheet at color, and then also at variety. Variety will just be a 1 through 6 in that case, into that array, into that table. And color will just be from 1 to 12, or 1 to 9 by, I think it's 9, I think it's 18. 1 through 18 is essentially the range of colors, which will allow you to choose, if red is 6 or whatever. Indexing into 6 will be that 6, will be that particular sub-row of red tiles, and the variant or the variety you can then choose by indexing into this latter part of the 2D array that offshoots off of this. Really, this is a 3D array, but the 2D array that we're concerned about is just these two branching off of G-frames tiles. So that's tile. Board is a bit more complicated. Board's got a lot more going on for it. It's got the actual initializer, very similar to what we've looked at previously, except now we'll see that our constructor for tile takes in a random number between 1 and 18, which is the color range, and then math.random6, which is the variant or variety range. So again, if we look at tile, that's what the constructor does here. Just takes an XY, a color, and a variety, and that's what gets stored here. And then here we can see that in initialized tiles, we want to also do something interesting, kind of. And that's, we want to calculate the matches right when we generate the tiles, because if we start the game and there's already matches, then we're sort of in this weird thing where we're going to start to see matches happening when we start gameplay. We didn't even do anything. So we want to make sure that we start on essentially a slate that is completely clean, that doesn't have any of these matches, that is ready for us to create matches. So what we can do is we can take a look at calculate matches. And essentially the logic here is that we're just going to reinitialize over and over again until we hit a point. Mathematically, it's very easy with the number of variants that there are right now. But in the world where you might have only a few variants, you might want to instead just perform the actual matches and then just keep the same board state and just repeat that over and over again until you get to a stable board state. That's going to be faster and easier than, at least in terms of processing for a smaller range of tiles, than this approach. This approach is just expedient, but ultimately isn't the ideal sort of, I think, for especially if you start to lower your range of tile colors and variants. But this calculate matches is what we essentially just took a look at in the slides, and that's what I want to focus on probably the most. This and a couple of other pieces throughout the rest of the lecture and what we talk about before signing things off and talking about the problem set. But calculate matches is essentially the logic that we exactly just talked about, which is, remember, again, the going through from the left to right, top to bottom. We're going to check how many contiguous tiles of the same color are there in a row on either of those axes. And then let's return those back to the calling bit of code. The calling bit of code is in play state. So in play state, there's going to be stuff happening. The user's going to move their cursor. They're going to highlight things exactly like we showed. The examples that we showed are very similar to what's actually in the code. But when we actually, and we'll take a look at a couple instances of where timer is relevant for the code as well. But if we go down here to at the very end of this part of the update function, so we'll see this is essentially if they press enter. So this is, again, basically kind of what we were looking at previously. But when they press enter, we're going to either highlight a tile and get ready to swap on the next enter click or unhighlight. Or what we're going to do is perform the actual swap. And then when we perform the actual swap, it's all the same stuff that we did previously. It's all the same sort of like moving the X and Y back and forth between the two, or unhighlighting things in that particular case we were just looking at. But all the swapping is basically the same code, all the same code. For the most part, even here, there's a tween, and in this case, we're doing it over 0.1 seconds between the two tiles. But once this tween is finished, once the two tiles have actually finished moving back and forth, we want to actually do self-calculate matches. So this gets called from play state after we've actually performed a tween, a move between two tiles. And we can do that from board, or actually, well, I should say, we're going to call boards calculate matches from self. In this case, self has a function called calculate matches. So let's take a look at that first. That's going to be more relevant. It wraps a couple of things. So the first thing that we'll do is we'll say, OK, let's get the matches back. Recall that we showed that in the slides. It was, we go through all of the process of going through X, Y. OK, do we have a match here? 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 Get all four in the case that we saw. We want to return those back to the play state because the important thing about matches is that they are effectively our score. Like the more matches we get, the tiles are each worth some amount of points. So what we can do is very simply just say, OK, if we did get matches back from board calculate matches, which we'll look at in a second, which is the bulk of the heavy lifting, we'll just, OK, for every match in pairs of matches, we'll just, whatever the length of that is, we'll multiply that by 50 and then add that to our score. That's it. That's all we have to do. And then after that, we'll do the remove matches step. We saw that. We alluded to that in the code, right? We'll remove the matches. So we need to actually set those tiles to nil, so we have these spaces. Then let's get the falling tiles, and that includes the tiles that are in the board. So the boards will actually, the tiles that are in the board will fall down, and they'll get displaced. And then the tiles will come up from the top of the ceiling and fall down. This will happen at the same time, so everything looks like it's moving in unison. And then essentially what we'll get back from this function is a set of tween operations, right? It's a set of XY interpolations. We can just pass that directly into tween. And then once that's finished, well, again, we're going to need to make sure that we don't have more matches left, because who knows what tiles are going to get generated. They're all random. So if there's more matches, well, let's just perform it again. And then this is a recursive function because self-calculate matches is the function that we're in right now. So if there are more matches, well, we're just going to keep doing this over and over and over again. And sometimes, again, some of the most fun you have in these kinds of games is just like putting together a smart match that just gives you a ton of points and just kind of ricochets and does all this stuff. But that's essentially how we're achieving this sort of infinitely processable swap operation. It's going to calculate the matches, get all the falling blocks, do all that stuff, and it's going to call itself again if it needs to, if there are matches that have to actually process. So the first step, the main step in calculate matches is going to be the actual boards calculate matches. So we won't spend maybe a terrible amount of time looking at it in tremendous detail. I'll go through it so that folks can follow along. So we won't take too much time doing it. But essentially, we're just going to go through every row. We're going to look through X and Y, right? Do we have horizontal matches? Is this color the same as the last one? OK. Was it also the same as the last one? OK. Yep. OK. We got at least 3. OK. And then once we get to the next color that's not the same color, cool. However many we had and that we were storing a reference to, let's take that away from, well, let's store it in a match and we're going to return it for points. But then also we're going to need to flag all those matches are going to get stored and they're going to get removed from the board as part of the remove matches function. So here we can see we have like a color that we're going to match, which is the first color in the loop. Every horizontal tile from 2 to 8, we don't need to calculate 1 because we already did that by default. We're just going to say, is it the same color? Is the tile there at yx the same color? And this is traditional with 2D arrays. In games, typically you're going to go based off of yx, because y being each row, right? Because if you go top to bottom, you're going one row at a time. So yx dot color will be whatever as we're going left to right, each row. If it's the same color, cool, increase the match number. And then if it's not, okay, well then now we need to change the color to be whatever this color is. Did we get at least 3 tiles? And if we did, let's create a match. Let's put it into a table, which we're going to insert into this matches table that we're going to return. And then we're going to go backwards from where we are currently in the match. And then we're going to insert the tiles that we had found up until this point into this table. And then this table is going to get added to a table that gets returned back. And then if we're at greater than or equal to 7 and it wasn't a match, we don't even need to worry about the last 2. It's impossible for 2 tiles that aren't part of a match at the end to be a match, so we just kind of shortcut the loop here. And we do the exact same thing for the vertical matches way down here. And then it's essentially how we get the entirety of all the matches. We just are iterating through the vertical, well, we're iterating horizontally by going down through each row, and then we're going through each column by going left to right. So we're going each column, and then within each column, we're able to look at all of the vertical tiles within that column to determine if we have any matches. And then once that's all done, if there's greater than 0 matches within the actual match table, we'll return it. Otherwise, we'll return false, at which point we can then use that in playstate. If playstate gets a falsy value from this function, it's not going to have any matches. We don't have to worry about it. It's not going to do anything. It's not going to actually do all of this code here, recall. But if it does, we want to remove the matches, which we're storing a self.matches reference to these matches for this purpose. So remove matches is simple. All it is essentially just for every match that we have, let's iterate through all the tiles and set them to nil in our table. The result of this is that we'll try to index into whatever that particular index was in our array. It's not going to be anything. It's going to be nil. So we don't have to worry about actually anything there. But then what we can do is add tiles to fill it and then interpolate them into those new positions. So they'll get erased because they won't exist. They'll lose that color value and won't be rendering. But the tiles above it will fall, and then the new tiles will come in to populate it. So that brings us to falling tiles, which is sort of the last piece of the puzzle, so to speak. Again, we're returning a tween table. We're saying, OK, we want this table to come back that's got all this tween information, which is x, y values in our case. So we're saying, OK, remember, we saw this visually, but we're just going to go through each column up until we hit the top of the ceiling, so to speak, of our grid, looking for spaces, and then looking for the nearest tile to bring down to that space, and then just kind of going up until we reach the top of the ceiling. So here we see we just have simple space. What's the y where our space was at? While y is greater than or equal to 1, so until we get to the top of we're assuming bottom would be 8, top would be 1. And then we're going to get the tile that's there. We're going to try to index into our array. If it's nil, then it's not going to be a tile. It's not going to be anything. And that's going to be where we should flag it as having a space if we haven't already. If there isn't a space and the tile is nil, let's set space to true. If space y is 0, then that means that it's not a space that we've actually found yet. So we can just assign our space y to 0, or rather our space y to y, and keep track of that. So as we go up, that's where we're going to need to make sure, like, for example, if there's a tile at the bottom, we need to make sure that we put the next tile and let's say there's a tile, a space, and then a space, and then a tile. We're going to want to make sure that we put that top tile not all the way at the bottom, but above the tile that existed there. So that's why we maintain a reference to the y that needs to exist there. And then in the event that we have a space flagged, but we find a tile when we're going up, well, then we'll just set that actual space Y area to be whatever that tile is. We'll set that tile to nil, setting the grid Y to be that whatever that space Y is that we had set. We're going to flag the tile itself, its grid Y to be that space Y. And then its actual, because that's its discrete spot in the grid, but its actual Y is going to go into this tween table. So this is going to move it down using its grid Y as a reference point, -1 because of coordinate-based access versus table-based 1 indexing, times 32, which is the tile size. And so this is just going to eventually accumulate a bunch of these tiles that need to move down. They all are going to be tiles that move down until we return at the very bottom the tween operation, or the table of tween operations. That's for the, in the case we're talking about right now, we're talking about the tiles that are already in the grid that need to move down to fill those spaces. But as we saw, the very last example visually illustrated was the top of the actual grid has spaces that needs to get filled with new tiles, which is how the game is sort of infinitely playable. The tiles that go away have to be replenished. And so we do that here. You know, again, from the top, we look down. Are there tiles at all in this, or are there spaces? And if we see spaces, we're going to count the number of spaces going from y equals 1 to y equals 8. And then we're just going to essentially add those to our tween operations. We're going to add them into the table, but we're also going to add a tween operation to them that has their y position tween from -32 is where it starts at to whatever its grid y -1 times 32 is. So it starts at the very top of the screen and then comes all the way back down to wherever its resting place is in the grid, which is going to be multiplied by 32 pixels. So all of that, and we'll just, again, visually illustrate it. Then we'll take a couple seconds just to, like, again, re-look at some of the other things, the tweening and timer-based things we looked at. But we'll move over here, see if I can get a match. But, you know, I'm moving around, so these grid X's and Y's, we've got this tile here. I want to move this here. The 3 tiles above it are going to tween down. 3 tiles above that are going to tween in to replace those tiles. So I do that. You can see that happen there. And then if I, let's say I move, if I can find a match, let's see, let's move. Kind of tricky sometimes. Okay, let's move this one here. So again, we're going to have a sort of, the red, purple, yellow are going to move down to fill this space, which they did indeed. And then we had 3 tiles that spawned above that. And then if you were to get sufficiently lucky or skilled at playing something like this and have many, many matches occurring and filling in the space, or rather, many, many matches that would sort of organically come up to be because you got a bunch of matches figured out somehow, you would essentially see this repeat over and over again. I'm going to restart it one more time because we should look at also, again, draw your attention to the transitions. The last 2 pieces that we'll look at are the transition between this state and the next state, and then also the sort of moving down of the level text, which are the last sort of pieces I think that are relatively new that represent the tweening and timer-based operations that we looked at. Let's go ahead and start this. So again, there's a, imagine here, you know, if you were to think about it, right, like how do we make this screen white, fully white? Well, there's not really an easy way to do that other than maybe a rectangle that we could draw to the screen on top of everything else that was just transparent and then transitions to full opacity, and that's exactly what we do. And then, you know, how do we go back from the next scene or the next state to, rather the transition at the start of that, how do we go from that to having the white sort of fade out? And that's just the same thing in reverse. If we just start that state with a fully opaque rectangle that's white and then just fade it to 0 opacity, well, we get this illusion that we've transitioned smoothly between these states. They've been like very actually still the same abrupt transition. It's just that we are like tricking the user, the viewer, into not seeing that through clever uses of timers. So here's the rectangle. It exists already. It's not being rendered. It's going to tween its opacity to 1. And then it starts off at 1 and tweens it to 0 in that begin game state. Then it gets the sort of level text transition down, and then transitioned at the very bottom. We'll go ahead and just see what that looks like here. I'm going to close these examples. And in particular, we care about the start state. because that's where we're going to keep the actual transition rectangle for the transition to the begin game state. If we look up here, rather it's down here, we have a transition alpha that's 0. And if we press enter, you'll see that we do indeed do a tween operation between self. In this case, you can pass self if you're within an object. You can do that. It'll just use whatever self.transition alpha is. And then transition that to 1. That'll go from 0 to 1 over 1 second. That's what this, remember, this initial argument is. And then again, at which point we've seen this. This is the chaining idea. This is at finish, an anonymous function that has our state machine change that takes us to level 1 of the begin game state. So we are including our state machine transition within this finish callback of the timer.tween operation, this new thing, these building blocks that we've put together this whole time. And then we're removing a color timer here because it maintains a reference to things that are going to not exist in this. You can remove timers from timer if you maintain a reference to them. If they're going to refer to values that won't exist at a certain point, this is good because you'll crash your game if you don't do that. It'll try to tween a value that gets deallocated effectively. But if we come down here, you'll see that we have a rectangle here that we just draw. It's a fill rectangle. The whole width of and height of the screen, we initially set transition alpha right before that. Rather, we set the color using transition alpha such that the rectangle gets drawn with that color, with that opacity. And then we remember to set our marker, our sort of global color tracker, to full 1, 1, 1, 1. And then, so the result of that is we transition to 1 over 1 second in opacity, which gets us to be full white, at which point we instantly transition to the begin game state. So once we open that up, this has its own transition alpha that's already set to 1, such that we can immediately, on enter, remember that all of these states expect an enter and an exit function. In this case, enter gets called right as soon as the state machine gets loaded into the state machine, the state object does. So we are going to just immediately begin the transition from 1 to 0 on this transition alpha. So we're essentially going from 0 to 1, cutting to a new state that has already pre-baked into it a transition alpha of 1, so it's a full rectangle that's white. At which point, once this is finished, we have a finish callback that's going to, over 0.25 seconds, move this thing called level label y down to halfway down the screen. That's the level, literally the label, the rectangle that's semi-transparent with the text in it. It's going to move it there. On finish, we're going to say after 1 second, let's tween. So this is like the timer.after we talked about. We haven't really seen after too many times. We saw timer.every. Timer.after, we just care about 1 second. I want to then trigger another tween of that same label text down towards the bottom of the screen. At which point, we can then call gStateMachineChange to play, and then we're in the play state. And then we can begin our game loop and do all that stuff, and everything is very smoothly and cleanly transitioned to and from each other. And I think that is the majority of all the pieces that you will need in order to do the problem set for match 3. It's quite a lot of pieces. There's a lot of various new time-based mechanics that we've talked about. And I think it would be kind of fun at the very end just to kind of look at a couple of things that are, I think that are important for me, at least when I'm thinking about games and aesthetics. It matter to, especially in 2D, but I think this applies globally. But we used deliberately a sprite sheet that is a limited palette sprite sheet that uses, I believe, this exact same palette, Dawnbreaker, which is a Dawnbringer 32 color palette. He has Dawnbringer. They have multiple different numbered colored palettes, but it's a very sort of famous at least in the retro community. And this one's really cool because the colors are created in a line such that you get a very tremendous gamut with only 32 colors using dithering. So this is essentially like pixel patterning the colors such that, like, if you mix any two colors and you off-color them in a particular way, you can get colors that look to the human eye as if they're actually between shades of color, these sort of larger palette shades of color. And so here, this is just, the 32 color by 32 color matrix in sequence, and it's quite impressive. It looks like a full range of color. But game art historically was palletized. In older consoles, there were limitations that made it such that color value, color size was only a certain size, and you had to have a certain bit depth for every pixel on screen that was represented in different ways depending on the console. But with just a very primitive, seemingly palette on the surface, you can achieve very nice aesthetic visuals and coherence to your design. It's kind of one of the benefits of it too, is that there's a mistake that you can make by choosing palettes that are overly rich sometimes, especially in art like this, where the just sheer number of choices leads to more opportunity for conflicts, for overly harsh contrasts on the eyes. And so if you have just a set of very well-designed colors, your risk of that is pretty minimal. And so it's common in games nowadays, I think in retro community especially, to try to use some of these ideas. And we used it today in all the Match 3 art. It was all 32-bit, or 32, just 32 colored, 32 color palette. This is an example of if you were to use the same palette on a real image, you can preserve almost all the detail. You do see some of the artifacting and some of the sort of weirdness of it, but like it's impressive what you can represent. And here's a better example. This is just a comic cover. This is the base color, and then if you apply Dawnbringer to it, the 32, this is what it looks like, and it's very little actual loss in color, but you still get like pretty much everything exactly as you would want it. And it's cool and impressive and super fun. And I think it's important to take that into consideration if you're developing a game. Try it as an exercise. Use only 16, 32, maybe even 8 colors, or be ambitious and use like 2 colors like Game Boy or 4 colors. It gets to be trickier that way, but it's interesting what comes about through limitations. This applies also, it's the same idea in palette swapping. So in consoles like the NES or the Super Nintendo, you would have a palette that's loaded in memory that can be swapped out, and then all of the sort of video work that's being done by, on the NES, it was the PPU, I believe, the picture processing unit or pixel processing unit, and it would be looking at this range of memory addresses for the colors that it would then draw onto the screen, and every piece of art that's on the screen would be therefore easily changeable on the fly to be some different color. And this is something that's used in a lot of retro games to good effect. Super Nintendo is a console that I loved and has a lot of instances of this, but it's just a cool technique, and it's related to the idea of palettes. It's essentially the same thing of having this set of 32, 16, 8 colors that are at that time in hardware, but nowadays in software, sort of like limited for aesthetic or functional purposes. So assignment 3 is going to be, so far what we've done is we've seen that by playing the game, you sort of have this hard set 60 seconds when you're playing, and it's pretty difficult. But it would be better if you could just add some time if you were to get matches, be actually incentivized and rewarded for your time or for your performance. So it'll be add the ability to get time added to your timer, rather refunded to you effectively, such that you can keep playing and not run the risk of losing quite so easily. The blocks that we saw so far were all using variants, but the problem set is going to encourage folks to use variants that scale up with difficulty and actually mean something for point multiplication. So rather than just having all of them be the same value, like take the flat block, have that be some value, and then incrementally add these variants as the level increases, as your performance throughout the game goes up, and then allow that to be a multiplier for how many points you get for that color. The sort of thing that I always think about when I think of Bejeweled, when I think about Candy Crush, is like these blocks or these candies or whatnot that have like just this explosive power or this board wiping effect. And this problem set's going to require that folks determine some block generate at random that has this shiny flag or that has some sort of variant on it that's visually different and allows you to destroy a whole row of blocks when that gets cleared out. And also, in addition to that, create some kind of a particle effect such that it's visually also represented on all of the tiles that it affects. Then right now, you can swap any 2 blocks that you want, but you should only be allowed to swap blocks when there's a match. And you should also calculate such that if there is no possible one swap that will result in a match, then you should restart the board or have the board reset. This is a thing that happens in Candy Crush and Bejeweled. If you can't do a swap that actually will give you a match, it'll just completely wipe the board for you and give you a whole new board that does have tiles that you can swap in order to create a match. So you'll want to do that. And then lastly, implement matching with the mouse. Right now, we don't have that ability. You just have to use the cursor, but Match 3 and Bejeweled, at least on phones, would typically be mobile games that you would use your cursor or your finger to actually create a match with. And so allow the ability to do that. And you'll need, as a hint here, in order for this to work well with virtual resolutions in the push library, you'll need this function, push.toGame of x, y. So next time, that's the problem set for this week, but next time, which is this certainly is one of my favorite lectures coming up, but a lot of the things that we talked about are going to be applicable, particularly for the maps and the idea of talking about tiles as IDs and having that be meaningful. But we're going to look at Mario, Super Mario Brothers, and we're going to look at an example here using artwork that is sort of open source, public domain art, a variant thereof, but a very robust tile set. But we'll be looking at tile maps, which is very similar to what we looked at with today's grid, except tile map is sort of this way of representing a world in 2D space, and then having your world be essentially subdivided, if in terms of like Minecraft does, in blocks, but in 2D, it was sort of like the original Minecraft in that sense, I suppose. But how does the sky differ from a block on the ground versus a bush versus a pipe or something? These are all going to be represented as tiles, which we will deal with collision and other things related to those. 2D animation. Your character should move around on the screen, but they can't be like a stiff, like just translating sprite. So we're going to need to animate movement and jumping and various things like that. Platformer level generation, we'll look at an actual meaningful procedural generation sort of approach and look at some really cool level designs we can get for free just through code, which will be exciting. And then platformer physics, which is just essentially an extension on AABB collision detection, but it has some slight differences in the world of platformers. And then we'll also look at hurt boxes for how to actually interact with enemies, and then lastly, power-ups and how those work and how we can use triggers to create them. So that was all for Match 3. It was a bit of a sort of return to modernity from last week. We've sort of gone back and forth and back and forth, and the next week we'll be going back again to Mario. But that era has so much nostalgia for me, Mario and Zelda and all these different games, so I'm very excited for that. This is CS50 2D, and this was Match 3. We'll see you next week.